collaborators at Maryland and in China and many other places. I'm trying to develop a nanostructured functional materials as electrocatalyst. And also we working on operando calculations. So basically this is kind of a tools we're trying to develop to enable us to probe the electrochemical reaction at the interface. This is critical for us to understand what's going on the surface of the catalyst. And from there, we're actually starting building device, trying to integrate the catalyst into a small scale. We look at the different cell configurations, and then we actually look into opportunities for scale up, multi-cell stacks, or on the bottom right is the two integrated two-step process. So a final piece of my research program is we also look into the tech economic analysis. This is something I also will cover a little bit in this particular talk. So what's the opportunities? I would say the biggest opportunity I see for the coming decades is we are going to have cheap electrons, and we need to be ready to take advantage of those cheap electrons, mostly from renewable sources. So how to use these electrons to drive chemical reaction is something I'm really passionate about. I think this is a great opportunity for us to work in this field. So once you have the electrons, what you can do? So in my research program, we mostly focus on the carbon utilization. Basically, we're trying to convert the carbon dioxide to useful chemicals. But you can think about other abundant source like nitrogen, water can be also transformed to hydrogen, ammonia, like carbon monoxide or ethanol, ethylene, a bunch of chemicals. And those chemicals can be eventually used as a fuel or can be integrated in our existing chemical production and manufacturing side. So I don't know the audience is all familiar with the electrochemical system. I just want to give you 2 minutes kind of introduction about the device, what kind of device we're working on. So electrochemical device use use a membrane material with 2 electrodes and the 2 catalysts, one on the anode side, one on the cathode side. On the anode side, usually we're dealing with is water oxidation reaction. Of course, you can do other oxidation reactions. For this particular talk, we mostly focus on the cathode side, which is a reduction reaction, or it's mostly important side for carbon dioxide transformation. So the benefit for this kind of system is you can easily couple with renewables, and this can be scaled from very small units to larger units. And we can operate these kind of units actually at near ambient conditions. So I'm going to use a lot of technical terms such as current density with a unit of milliamperes per centimeter. Basically, it's reaction rate or potential. Sometimes I call it voltage. This is more or less related to the energy input. And the fire decay efficiency basically is talking about the number of electrons goes to the desired product versus the total electron pass through the system. Basically is the selectivity. So what I see in this particular system, which we call a polymer membrane-based electrolyzer or low temperature electrolyzer, I see this, the major challenge is the carbonate. I think in recent years, people notice these kind of issues is CO2 is acidic gas. When you use CO2 and also coupling with the alkaline electrolyte is kind of popular at the moment because it can efficiently suppress the hydrogen evolution and also promote the carbon-carbon coupling reaction. So you can actually make an interesting multi-carbon product. But the problem of alkaline electrolyte is CO2 will react with the hydroxide and form carbonates and bicarbonates. So basically, you actually consume your electrolyte. So this kind of a process become not sustainable. So if you look at just stoichiometrics, if you take one CO2, do two electron reduction, make a carbon monoxide, you generate two equivalent amount of hydroxide. Basically, that will consume one CO2 molecule from one carbonate. Basically, you will get into a situation is about 50% CO2 utilization in this particular system. So this is our recent study on the top right is a figure just showing you the fraction of CO2 you feed into the system versus the percentage converted to carbon monoxide. So depends on different flow rate. We're actually using is very diluted neutral pH electrolyte. Even with the neutral pH electrolyte like sodium bicarbonate, we still get up to only like 45% of conversion. So basically the majority of the rest of CO2 you feed into the system actually form is bicarbonate or carbonates. This kind of situation even worse for multi-carbon product. If you just do a stoichiometric analysis, right? If I want to make one ethylene, I need a 2 CO2 molecule. That's 12 electron transfer, and you make a 12 hydroxide. And 12 hydroxide will consume 6 CO2. So if you do the calculation, that limit your overall conversion to only 25%. So how do you actually address these kind of issues? So the very recent 2 years we actually mostly focus on is we call the two-step process. We try to decouple the CO2 initial conversion with multi-carbon product formation. So we basically is convert the CO2 to CO, the carbon monoxide to multi-carbon product. So there are recent development, particularly on solid oxide, high temperature route for electrolysis. There's a lot of progress that has been made, and the durability now up to almost 1,000 hours. And they can very selectively make carbon monoxide from carbon dioxide using this high temperature electrolysis process. And that kind of particular process don't have this carbonate formation issue because they actually use a ceramic membrane rather than we use the aqueous solution plus the polymer membranes. And for CO reduction side, we can take advantage is the CO doesn't actually react with the hydroxide. So that is perfect to operate in alkaline electrolyte and take advantage of this high pH system. So I'm going to tell you a little bit about the initial result and what's our general approach really promote this kind of reaction. So for CO reduction, so I want to first share with you a little bit the insight, say why we come with this particular design. We call the how to play with this hydrophobicity at the interface in order to enhance the reaction rate. If you take a textbook kind of figure, this is I took from one of my favorite textbook is the physical electrochemistry. So when you configure electrochemical interface, you have this gas, solid electrode, and the liquid electrolyte interface. Your reactant is gas, okay? Usually gas has pretty low solubility in aqueous. So how to achieve a high reaction rate? You have to optimize the liquid electrolyte layer thickness. So on the middle top is this, the dashed line represent the current profile. And you can see the current actual peak at middle of this figure, this chart. So basically, if you have a liquid layer too thin, although the gas transfer could be very fast, but the charge transfer become limited. When you have very thick liquid electrolyte layer, then gas diffusion become limited, although the charge transfer could be fast. So there's a sweet kind of a spot. You have to optimize this kind of thickness. In reality, how we play with this is to play with the hydrophobicity of your interface. So oftentimes we utilize is carbon support, we call the GDL, carbon gas diffusion layer. And play with the hydrophobicity of the gas diffusion layer will allow you to achieve these optimum conditions for CO, which has extremely low solubility in aqueous, but we still can achieve very high conversion reaction rate. So on the bottom left is the cell configuration. We use three compartment cell configuration. Top one just feed the CO2, CO gas. Then we have the catalyst layer deposited on hydrophobic carbon support, cathode, KOH electrolyte, and then membrane, which we use is anion exchange membrane, and then another KOH as a supporting electrolyte for the anode side. So with this kind of cell configuration, what we can achieve is pretty decent current density, up to almost 1 amp per square centimeter. Just give you a sort of a background what this current density really mean. For commercial water electrolyzer, basically they are operate roughly 1.5 amp to 2 amps per square centimeter. So we're actually very close to that kind of a current density. And also very importantly is we actually can achieve at the same time over 80% multi-carbon selectivity. Okay, this is kind of important. It's not just the high reaction rate, but also good selectivity. And if you look at the right chart, we use a micron-sized particle, okay? Nothing fancy about the catalyst in this particular work. But we still can get a lot of ethylene and acetate, ethanol are the other major product, and some propanol as a C2 product. So this is one of the working systems we actually very recently assembled and tested out. I just want to share with you what we actually did very recently is we successfully to demonstrate this two-step process actually can work in the lab environment. And on the left is the, let me see how to use the laser point. So on the left, this is the CO2 electrolyzer, which has a 100 square centimeter size. And this is the multi-cell stack for CO electrolysis. And also we have other units like pumps, like a pressure controller, liquid trap, and also the flow control systems. So let me quickly jump to this performance. So this is the voltage profiles for these two units. They work actually in a tandem fashion. And over the 3 hours period of time, for this particular work, because it's DOE funded, we mostly look into the alcohol, but the rest of our products mostly is acetate and ethylene. And you can see what we can achieve now is very stable current profile. For CO2 electrolyzer, we can operate at 7.5 amp, and for CO electrolyzer, we can operate at 10 amp. Actually, this is the two-step process we actually demonstrate about 2 months ago. So I also want to bring up this kind of a challenge is most of the time we work in the lab, we use a pure CO2, but in reality, we are not really have this highly pure CO2 source. So we have to dealing with like CO2 emission from a power plant, for example. And in those kind of carbon dioxide source, we have to dealing with this SOx, NOx contaminants. So we have recent 2 years looking into how these contaminants can affect the electrolyzer performance. For example, silver, tin, copper are the most commonly studied catalysts for CO, formate, and multi-carbon product production. So first of all, I want to talk a little bit about the SO2. SO2 is pretty nasty gas. I think most of the, if you talk electrochemists, they don't like it. I think even if you work a heterogeneous catalysis, you don't like SO2. So when you feed a little bit of SO2 into the system, this is on the left is what we did a flow cell test. We first half hour, we just feed a pure CO2. Then we switch to a CO2 plus 1% of SO2 gas feed. Then we stop and restore the pure CO2 gas feed and look at the selectivity performance and also look at the voltage profile. The voltage actually is pretty stable, relatively stable. don't have any significant change. But if you look at the Friday efficiency, those bars actually dropped when you feed SO2. The reason for that is SO2 also got electrochemically reduced on the surface of the catalyst. That's why you lost the electrons to this undesigned reaction versus what you're trying to do is the CO2 reduction to CO for silver catalyst. But fortunately is once you restore the pure CO2, the selectivity doesn't change dramatically. And you have a little bit more hydrogen. I think it could be introduced from the surface polymer sites on silver catalyst. If you look at the tin catalyst, tin is a formate selective catalyst. So if you feed a pure CO2, you basically get over 90% just the formate. Okay, this is definitely what we expected. Once you have 1% of SO2, the Friday efficiency actually dropped pretty significantly. And this is also caused by this SO2 reduction on the surface of a tin catalyst. And once you stop feeding SO2 and just using pure CO2, tin actually also has a very good property, you can say tolerance of SO2. So the selectivity doesn't change very much, which is kind of a good news, right? So at least silver tin, they don't have very high sensitivity of to this SO2 contaminant. But bad news is copper. Copper is probably the most interesting catalyst in CO2 electrolysis, electrocatalysis community because it's a unique capability to make a multi-carbon product. So at the very beginning, we make a lot of CO, ethylene, formate, acetate, propanol, ethanol. But once you have SO2 in the system, all of a sudden, you only produce almost just two things. One is hydrogen, the other is formate. Basically, you eliminate all these multi-carbon product. And even you stop feeding SO2, and the selectivity doesn't restore even after 5 hours continuous electrolysis. Basically, this kind of a study actually showing you is copper is extremely sensitive to SO2 contaminants. So if you're trying to design a reactor system for CO2 conversion, but you have to dealing with the source contain SO2, I think the strategy, the information here is you have to take care of the SO2 before you feed into the system. So this copper actually is extremely sensitive. Even you reduce 1% of SO2 to 0.01% of SO2, and you can see that the impact is still dramatic, okay? We actually did some post-reaction XPS analysis. We found on the surface, you actually form this copper sulfide species, and there's a lot of sulfur deposit on the surface. I think that actually is the reason why we see a dramatic change of the selectivity in this particular system. So then we actually move on to look into the other contaminants, commonly contaminates in these point sources is NOx. So this particular slide actually is showing you just the NO, which is one of the dominant contaminants of the NOx in this flow gas. So when we feed about 1%, 0.8% of NO into the system, we see similar phenomenon, a big loss of Friday efficiency. This is mostly because of NO got also electrochemically reduced on the surface of a catalyst. So on the left is copper, on the right is silver catalyst. You basically observe is the similar behavior. The good thing about the NOx is NOx doesn't stay on the surface even it's reduced. So either it reduced to ammonia, it reduced to nitrogen, it will actually leave the system. So, and that's why if you restore the feed into a pure CO2, all the selectivity stay as exactly the same as before, okay? So the take-home message here is NOx is not something particularly you need to worry about. I think SO2 will definitely have a much big impact, particularly on copper catalysts. So I want to move on to a sort of a related topic. I feel this is more of opportunity side. I'm talking about a lot of problems. I don't want to just say, hey, there's no hope to make this work. So I want to share with you some of the new things we can do about this. So the community right now at the moment, mostly focus on is carbon-carbon bond formation. So we're trying to make this multi-carbon product. And we see this is a very interesting chemistry we can do. This actually is a very unique feature about the low temperature route. And if you're talking about a high temperature CO2 electrolysis, you're basically stuck with carbon monoxide. So we look at this carbon-carbon formation and look at the chemicals we can make. We basically stuck with acetic acid, ethanol, ethylene. That's all we basically can make. Propanol we can make, but with very low selectivity. So kind of a thought here is, can we make a different bond, like a carbon-nitrogen bond in this kind of system? So the answer is yes, we actually can do that, is by introduce, say, ammonia. Ammonia is a nucleophilic agent. What we discovered is if you feed a strong nucleophilic agent to the system, which actually allows you to attack this ketone intermediate in this carbon dioxide reduction or carbon monoxide reduction reaction. And that will allow you to form this carbon nitrogen bond, and eventually it will lead to a unique product we call the acetic acetate amine system. So this idea we started about 2 years ago. This is a collaboration between us and Bill Gardner and Caltech. They did all the computational work I'm going to share with you in a minute. Basically what we did is, I call it the co-electrolysis strategy. Basically, because this is 3-compartment cell design, if you still remember in the early part of this talk, I introduced you, the top chamber we feed the reactant. Usually we feed just a pure CO2 or pure CO. In this particular case, we actually feed with a mixture of CO and ammonia. So because ammonia is a base and CO doesn't react with base, so we take advantage of that. And what we found is this actually is a very efficient ways to form this amine in the system. So other conditions is we control the ratio 2:1 to ammonia 1 CO ratio, and we use is a copper nanoparticle catalyst, and with 1 mole of KOH as a supporting electrolyte. On the right is basically the product distribution. Very interestingly, when you feed ammonia to the system, we actually observe a large quantity of amine, up to about 40% in terms of Faraday efficiency. And this kind of efficiency can be achieved at 300 milliamp per square centimeter. It's pretty decent reaction rate. And also we found is the ethylene alcohol formation, particularly alcohol formation, got suppressed in the system. So the next step actually is work with Bill Gardner group at Caltech, trying to figure out what's going on and trying to have a better understanding of the reaction mechanism. So the first thing we actually did is isotope labeling, trying to just confirm the amine we formed actually is coming from the CO we feed into the system. So we did the oxygen labeled CO study, and we found when we feed a O18 labeled CO, the mass actually shifted 2 units in the mass spectrum, which confirm the oxygen in this amine actually is indeed coming from CO. So also what we did, the other study is trying to alter the KOH concentration. What we found is when you increase the KOH concentration, the amide selectivity, molar fraction basically, is decreased when you go more concentrated KOH. So in other words, amine formation, they are not favorable under highly alkaline conditions. So our hypothesis at that time is somehow the ammonia and hydroxide compete with this ketone intermediate. This is a hypothesis because in the experimental side, we have difficulty, even now, we still don't have any technique which allow us to see ketone directly because ketone is so reactive species. They actually react even with water rapidly. So fortunately, we can work with computational groups and trying to understand what's going on the surface of catalyst. So this is one of the maps we put together. So just to be honest with everyone in the room, I won't say this is 100% correct, but I will say is this is consistent with all the experiment data we observed. So of course, these rooms to debate which this particular species is exactly the same structure or slightly different structure. Those things I think can be debated. So basically, I want to share with you is the kind of the thought, how we can actually propose a mechanism actually feeding all the experiment data. So basically, in the community, we have a consensus on the CC coupling step is the rate limiting step for C2 products formation. And once they couple, they will form this HOCCOH kind of intermediate. Then this particular intermediate can go two different routes. Either dehydrate, form this ketone intermediate, and this ketone intermediate, ketone chemistry is pretty old chemistry back to 50 years ago or 60 years ago. People know this particular species actually is very reactive when you have a nucleophile around. For example, hydroxide or ammonia, they both are nucleophile, so they can either hydroxide attack this ketone, you form is acetate. If it's ammonia attack this amine, you actually form is amine. So on the other route is the electrochemical driven process. You actually eventually reduce this intermediate into ethylene or alcohol. So this is sort of consistent with computational modeling efforts, but we're actually trying to further understand this is really solid kind of mechanism or still can be debated. So one of the study we did is trying to introduce species with different nucleophile strengths, okay? If our mechanism is right, basically is this step actually determine we form acetate or we form amine. If this is true, if I have a very strong nucleophile here to replace ammonia, I should have this pathway dominate and I should suppress just acetate, right? So this is one of the studies we did is using different kind of amine group with a methane group, ethane group. So basically we all observe is the corresponding amine formation in the system. And also if we use two methane group, that will make it more strong. And also we form the corresponding amine. So if we plot all the data together, y-axis is the molar production fraction, and x-axis is different amine, starting from ammonia all the way to diamethane amine, and look at the nucleophile strengths and how this product distribution looks like. So interestingly, what we found is when you go more and more stronger nucleophile, you get more and more amine and also less and less acetate, which is kind of consistent with our proposed mechanism. And for ethylene and alcohol, they more or less stay as the same. So if you go back to the mechanism, so this particular pathway actually doesn't strongly affected by what kind of nucleophile you put here, but acetate got suppressed. So we sort of at that time very happy with this mechanism because it's actually nicely explained all these experiment results we observe. And so we actually go one step further looking into okay, now we can build a carbon-nitrogen bond. Can we build other function group into this CO2 or CO-derived species? So what we did is to put a two function group, like a OH group and NH2 groups. And interestingly, only this side actually react with this CH3CO function group, which is derived from CO. And you can see the rest of the part actually stay as the same. And you can use, you can even replace with the COH function group as also stay on the same building block. So basically, I want to convince you is, start with CO2 or CO. You actually can do some very interesting chemistry here. And I think this kind of space is not well explored, and there's plenty of opportunities for everyone to move in and trying to figure out what kind of different, more valuable chemicals you can make from CO2. So finally, I want to spend about 10-15 minutes just briefly talking about tech economic analysis. I think this is a very important topic. Our group involved starting about 3 years ago. Now actually we keep on doing some more in-depth kind of analysis, trying to understand the key technological gaps in this particular technology. So if you look at the literature reports, you will get a sense is C1 product usually have very decent selectivity. For example, carbon monoxide, for example, formic acid, they actually can achieve close to 100%, 90-95% selectivity. And if you look at C2 product, ethylene is the only one people reported close to 75% selectivity, but the rest of the product like acetic acid, we are the group actually reported 50%. Ethanol is also kind of suffering from these high selectivity issues. So, and also if you look at the membrane systems, we have an anion exchange membrane, proton exchange membrane design, and the bipolar membrane design, and other designs. So this is one of the analysis actually help us to sort of sit down and look at all the existing data, figure out what's the key problem we have to address. So first of all, I want to share with you is just sensitivity analysis, okay? So the 4 major products we can make out of CO2 at the moment is carbon monoxide, formic acid, ethylene, ethanol, okay? And if you look at just carbon monoxide, formic acid, ethylene, and ethanol, what you will find is electricity price is pretty sensitive, okay? Their costs are very sensitive to electricity price. This actually makes sense because electricity is a driving force for this particular system. And this is the energy uphill kind of reaction. So if, depends on if you produce ethylene, you have to dump a lot of electricity to it. That's why in this ethylene case, electricity price actually is the dominant factor. And also, and you will find is a selectivity, single pass conversion, they also are a very important factor to bring the cost down. And so if you look at just from the cost perspective, what we see this particularly CO2 electrolysis technology is C1 product production is economically viable, but C2 products is still have some space to improve, I would say, in order to get to a practical system and with cost effective to compete with the existing technology. I take the ethanol as one particular example. I think there's a lot of interest in ethylene and ethanol because they are the 2 major multi-carbon products we can produce from CO2 using this low temperature electrolysis route. So based on our own analysis, we just finished this analysis. We haven't even published this yet. So with the base case is 2.5 volt cell voltage, 500 milliamp per square centimeter current density, 15% single pass conversion, 60% selectivity, and 3 cents kilowatt hour electricity price. And also we factor in the durability factor. So we basically assume every year you have to replace the MEA. And also we put a cost on CO2, $40 per ton. basically is roughly the capture cost of CO2. So if you put this base case, the ethanol production cost is, required selling price is about $2 per kilogram. That's way too high, okay? That's way higher than the current market price, which is roughly $0.5-ish. And there are a lot of things you can do to improve it, okay? So I won't say there's no hope at all, but you can see the water flow, actually you can actually eventually bring down to $0.37 per kilogram. So what you can do here? Cell performance. What if you can improve the selectivity to 80%, okay? 60%, 80% actually make a huge difference. And also what about the energetic efficiency? If you improve the energetic efficiency to 50%, so then that will actually will make the cost much lower. That's about $0.8 per kilogram. And if you improve the current density to 1 amp per square centimeter, that will bring another $0.24 per kilogram. What about the electricity price? Because in the base case, we already assume it's 3 cents per kilowatt hour. I think it's a little bit already optimistic. So if you have an even cheaper electricity, good news for you. If you have 2 cents or 1 cent, that will bring you additional cost saving. Eventually, I think durability is a big factor here. 1 year, 5 year actually have some significant difference here. This is a space, I think, as an academia group, we don't really look closely enough into this, how we can develop some type of protocol to accelerate this durability test in academic environment. I think this is definitely an area for research groups should look closely. And also, of course, at the end of the day, I think a policy also will play an important role here. And also, if you consider selling other byproducts from the particular process, for example, selling hydrogen will also help you to bring down some of the costs, like $0.13 per kilogram. And eventually, you can meet this target and beat this existing technology from fermentation process for ethanol production. So, finally, I want to bring up this issue is very recently we realized, people are very interested in electrolysis. People always claim when we have renewables, we definitely can drive this reaction, which is true. But the reality is our energy grid or electricity grid in the United States is extremely dirty at the moment. So if you do a life cycle assessment and take just the 2025 capacity expansion US mix profile, which is we use in this open LCA software. If you take that electricity and do analysis, this is a GWP, which is a global warming potential, basically is telling you how much CO2 emission will be. And this is much significant with the electrochemical process compared to the existing production process. So in other words, is if you look at these emission contributors here, basically the major contribution is from the electricity. So if you have a dirty electricity to start with, then I will say CO2 electrolysis won't help you to reduce the CO2 emission. It will make it worse, okay? And if you have renewables, and if say in the future we have a lot of renewables, if you get to 80% of renewables, that will make to the break-even point. So the proposal process will matches the comparison process, which is the existing process. And if you have a higher renewables than 80%, you actually have a much less CO2 emission compared to the existing technology. So last minute kind of summary, if you just outlook at the whole field and say what's the really opportunities, I would say really depends on what kind of market you're trying to address. If you really think CO2 electrolysis is a technology eventually will partially address the CO2 emission issue, at the end of the day, you have to address is on the left is the commodity chemical production. Basically, ethylene, ethanol, acetic acid will contribute to this CO2 emission reduction. That will eventually lead to plastic fuels and feedstocks for other chemical process. But if you look at this cost from the cost or economic perspective, for the immediate future, what's the market opportunities? I would say specialty chemicals for pharmaceuticals or other applications could have a better chance because the margin is much larger, and although the volume is small, but that actually can tolerate, for example, very expensive cells component, and it can also tolerate a high electricity price because the market price is much higher than commodity chemicals. And finally, I want to thank my research group. I have a lovely research group. A lot of people work very hard in the lab. And also, I want to thank collaborators all over the world. And this particularly study, we actually show you some of the work with Bill Gardner, and hope you're enjoying the talk. And also, of course, the Feng Jiao ADC, most of the work I present today is funded through DOE Fossil Energy Office, and also from NSF, National Science Foundation, CBAT program. And thank you for listening. I'm more than happy to answer any question you may have.
Thank you, Dr. Jiao. Let's give Dr. Jiao a round of applause for his beautiful talk. Thank you so much. Dr. Jiao, there are several questions from the chat box. Do you wish to answer them first?
Okay, sure. Let me see. Can you comment? Oh, yes, sorry. I saw the last one is, can you comment on the full cell efficiency for two-step process, slide 11. Let me see, quickly go to that one, sorry. So if you look at the cell voltage for CO2, basically the thermodynamic potential is about 1.3 or 1.4 volts. So this for the first step is about 40%-ish, slightly lower actually than 40%, so 30%, 40% efficiency. But the second process actually, now we can actually do much better than this one. This is from a couple months ago. But at the 2.7-ish volt and versus the thermodynamic potential, this is roughly 45%. So the overall process, I would say somewhere between 30%, could be lower than that. But this is definitely one of the areas we're trying to improve. And also, I forgot to comment on it. The efficiency actually is quite limited by the oxidation side of reactions. There's a lot of interest to replace the oxygen evolution reaction with other interesting reactions we can do. Let me see.
Feng, can I ask? There is a first question by Dong Ma asking about the comments, the stability of copper catalyst. If you move up, rolling up, the first question.
I don't see it. Can you read it to me so I can answer it directly?
Could you please comment on the stability of copper catalyst? This seems not to take into consideration of the performance and the economic cost if the catalysts do not have a long time.
So that's a great question. So the short answer is we don't know how long it will survive, and a long answer is we run up to like 10 hours, 20 hours. The longest reaction we run, not the copper catalyst, but silver catalyst, we run up to 100 hours. In that kind of test, we don't see degradation of the catalyst. And the major problem is actually the major problem of durability is not the catalyst, actually is the membrane. Membrane is one of the netman for these low temperature systems. There's a lot of work need to be done in order to improve the durability for membrane materials.